My name is Tom. I'm going to be talking about Gabriel's theorem. And my presentation is not on any specific paper. It's sort of just on the theory of the theorem and theory of the theorem. And how it kind of works. When you're thinking about when we're talking about this theorem, we should be thinking about at the beginning of the course, when we were looking at quiver diagrams, and we were breaking them down into we were tracking basis elements, and we were seeing when they were born and when they died, and when one died and we needed a new one, then we created a new one, and that was a birth, and then we tracked that one until that died. And so what we're really going to be establishing today is why you can do that, and why just tracking those basis elements gives you a full picture of the quiver. And why this is really important is because as we saw in James's talk, you can really understand, you can do a lot of theory by just looking at these birth and death times and analyzing how they work, the spaces. And that's all because somehow, which we'll establish today, just looking at those birth and death times gives you a total picture. To talk about this, we're going to need to know a little bit of representation theory. So my slides are going to establish some important ideas. So if we have a quiver, which is this upper diagram, then a representation V of that quiver is finite dimensional k vector spaces, which are for each vertex. So if you remember in our diagram, we had like R3, R6, R4. So those vector spaces are your vertices, and then we have linear maps from vertice to vertice. And so that establishes a representation of the quiver.
Is commutativity required?
Commutativity
Of that kind of diagram?
Commutativity is required, which...
Okay.
A morphism of a representation is a map between representations, and it commutes if the arrows commute in this diagram, and that's going to be a necessary condition. So composition is defined in the natural way that you expect it to be, and if everything commutes, then we have a representation. So yes, there is a commutative requirement. A sub-representation is given by a subspace whose image gets set to the image of a subspace. It's closed. And so what we're really looking for when we're talking about subspaces is irreducible subspaces. And so a definition of that is if you find the subspace of an irreducible, it's either the zero subspace or itself. So it's kind of this idea, this notion that we have about irreducibles in like rings and fields and other branches of math. So you can't really break it down any further unless you're breaking it down to itself or zero. Let's see. And then a sequence of representations is a short exact sequence if for each vertex in Q, the image of UI is the kernel of the next map. So this is the idea of exactness that we established at the very beginning of the course. And so we're going to need to remember that concept. And so what Gabriel's theorem says is that breaking down these AN type quivers, which are just linear quivers, so just a straight line of maps, that the irreducibles are just the intervals, the birth and death times of these basis elements. And so with that, I'm going to start building up a diagram on the board to understand why this is the case.
Just out of curiosity, do you know what happens if you don't have an AN type quiver? Would
Gabriel say, prove anything about that? Because there are lots of other Dickon diagrams that have nice representation theory associated with
I don't believe that there's anything in
it. And Gabriel's
Gabriel's
book.
theorem.
Yeah.
There's a part 1 which I don't think says very much, other than maybe, yeah.
Okay, so as I said, out of curiosity.
Yeah, I think part 1 is just discussing the exactness, and then part 2 is about this. Okay, so if we have a quiver that's going from some chain I think it has to start with 0. But, so if we have this sequence of maps, then what we're thinking about here is a sub-representation of this, where at some point we have an element that's born, and then we have identity maps until there's some point at which time it dies, and then we kill it to 0. And so this is like when we were tracking our basis elements, we would have created a basis element here, and then in these maps, that basis element would have been in the image of a map, and then we would have applied the next map to what that image was, and then it would still be there, and then here, it would have been in the kernel, and so it would have disappeared. And then we have maps down from our space down onto these sub-representations. Now, what's key here is that this lower representation is a sub-representation, which we'll call M1, is an irreducible representation. And it's a sub-representation with rank 1. And so it's an irreducible representation. And what that means is that we can construct a sub-representation up here that is, so we'll call them the W's. And we're going to define this sub-representation as the quotient of the, so this is, well, isomorphic to the quotient of the decay mod what this is. So like here it would be 0, but once our element is born, then it's isomorphic to the A-1 mod, our element, and so all of these isomorphisms continue to exist, and then it's killed, and it's back to mod 0, which means it's the whole space in that case. Okay, and so what we now have, if you imagine a line of all zeros down here, and a line of all zeros at the very top, then each of these are, from one slide prior, exact sequences.
Each column.
Each column, yeah. Each column is an exact sequence. So 0 to this sub-representation on that sub-representation 0. And so you can see how if this map sends the whole space to just our irreducible sub-representation, then this sub-representation that we've constructed up here is everything except for that. So therefore, the image of this is going to be exactly the kernel of this map. And so the great thing about this is that this means that we can split our representation here into the direct sum of our two sub-representations.
Yeah. The key thing is you can't normally do this with modules.
Right, and so I'll show you an example of why this doesn't necessarily always work. But just to continue the train of thought, we've now split this. And what's great is that this is irreducible, which means that this can't be broken down any further, but we've shown that this technique works. So by induction, this other part, that is the rest of the space, we can continue this process on this part. So this becomes the new m, and now we're going to look at new birth and death time of another element, and then that's going to split what's left. So that's going to split m2, and so we're going to have a new irreducible, so it's going to be the direct sum of three things. And then we can continue doing that until we've broken it down into entirely into irreducibles. And then at that point, we've completely deconstructed the space. And what have we deconstructed it into? Just the intervals of the birth and death times. So by breaking down our space into these irreducible representations, that means that we can understand the entirety of the space by understanding what happens to these irreducible chunks. Because these irreducible sub-representations form the entire space. Now, just because you're questioning me on why we need this condition for it to split, and why we need this irreducible condition, I'll give you an example of a map of morphisms, or morphism of modules that don't split. Okay, so if we consider the short exact sequence 0 to Z to Z2. Yeah, okay. So first, let's establish that this is a short exact sequence. So Z2 is just 0 or 1. And then Z is obviously all integers, and 2Z is all even integers. So if we look at the composition of this map, mapping the even integers to the integers, just a natural map, sending them to themselves. So the image of this is all even integers, and then the image of this map of the even integers is the kernel. The image of this map in here is in the kernel of this map, because all the even integers get sent to 0 in Z2. So we have a short exact sequence, but this is not irreducible. And so since it's not irreducible, this is not true.
Crossing
Yeah,
it.
yeah, sorry. Yeah, so this does not split, and it's because this is irreducible. This has rank 0. It's not an irreducible of Z. And so that's why the condition, that's why we're looking at just the birth and death times, because that happens to be irreducible. So this is a constructive proof. We know what the answer is, and then we're proving why it's the answer afterwards. We're not like arriving at that answer through linear logic that delivers us there. We know what the answer is, and so then we're constructing a proof of why that has to be the answer. And yeah, so that's Gabriel's theorem, and that's really the foundation for why we can just study the the birth and death times, and that gives us an idea of the whole space.
Great, thank you. Right, you had a question.
When you drew the first diagram, the big one, so you wrote like bold-faced ones at the bottom?
Yeah.
That was like one basis vector?
Yeah, it's like one basis vector. It's a one-dimensional self-representation.
It's a one-dimensional vector space.
Vector space, yeah. So it's like any scalar multiple of a basis vector.
Which is why in your code, you just track that one basis vector as a single bar.
Alright.
And so, if you want to think in terms of vector spaces, how it works is like, if we're in three-dimensional space, and we are tracking just like a basis vector, then, so this basis vector is our irreducible component, and then the rest of the space would be the perpendicular plane to that vector, because when you're working in vector spaces like this, then you can break the space up through orthogonality. So just the rest of the space, if you're using one basis vector, is the orthogonal complement, and so that would be the W's that were up top. And so then you can keep breaking them down until you have three vectors that span the entire space, and studying those vectors is the same as studying the whole space.
Any other questions? Yeah, Dave.
When you talk about like the rank of a vector space,
Dimension.
oh, okay.
Yeah, so when we're working with modules, we call it rank. It's a historical reason.
Okay.
Yeah, it's like if you think of a matrix, the rank of that matrix, it's the number of leading coefficients, and so that's the same as dimension if you're thinking in vectors, but if you're not thinking in vectors, then the more general term is rank. Yeah.
Awesome. Okay, all right.